Hi, welcome to the Random Walk and Bayes Theorem, Part 3. This is the third video in a three-part series on the Random Walk and Bayes Theorem. In Part 1, we looked at a case where an object followed a four-step random walk, but where the starting location of the random walk was chosen from two possible positions with equal probabilities. In Part 2, we saw how our results were related to Bayes' theorem and saw the role played by prior probabilities. Here, we'll again look at an object undergoing a four-step random walk. We'll take there to be several possible starting locations of the object, all in some given range. We'll take all possible starting locations within that range to have the same prior probability. Then we'll calculate the probability given the object's ending location of each of the possible starting locations. We'll again tie our results to Bayes' theorem. The example we do here can be treated as a schematic for understanding measurement uncertainties. So this example will function as a warm-up exercise if you decide to watch How to Interpret a Scientific Measurement with Gaussian Error Bars, or the videos in the playlist Why Bayes' Theorem is Important, available on this channel. So this video will lean heavily on the content of parts 1 and 2. So it's recommended that you watch those videos before continuing here. Okay, let's get started. Again, we're going to have an object that moves according to a random walk. I will randomly choose to start the object at x equals -4, x equals -2, x equals 0, x equals +2, or x equals +4, all with equal probability. I won't tell you where the object started. Again, the object will take 4 steps, each of size 1, either to the left or right with equal probability. After 4 steps, the object is at x equals 0. Given that the object ended up at x equals 0, what are the probabilities of each of the possible starting locations? Okay. So we want the probabilities of each of the possible starting locations, given that the object ended up at x equals 0. So this means we want to calculate the probability that the object started at -4, given that it ended at 0, the probability that it started at -2, given that it ended at 0, the probability that it started at 0, given that it ended at 0, the probability that it started at +2, given that it ended at 0, and the probability that it started at +4, given that it ended at 0. In order to find these quantities, let's first look at something else. Let's look at the probabilities of the object ending up at each of the possible ending locations individually for each starting point. We saw these distributions for starting points of x equals -2, 0, and +2 in parts 1 and 2. Here, we'll also include the cases where the object starts at x equals + and -4. Here, we plot the probabilities for the object to end up at position x if it started at -4. So that's the probability that it ends at x given that it started at minus 4. This is like the plots we saw in parts 1 and 2, but shifted to be centered at x equals minus 4. Note that the heights of the bins are the same as we saw before. So the probability that the object ends at minus 4, given that it started at minus 4, is equal to 6/16. The probability that it ends at minus 6, given that it started at minus 4, and the probability that it ends at minus 2, given that it started at minus 4, are both 4/16. And the probability that it will end at minus 8, given that it started at minus 4, and the probability that it will end at 0, given that it started at minus 4, are both 1/16. As we're interested in the case where the object ends up at x equals 0, marked here with a red arrow, we are particularly interested in the last of these. So the probability that the object will end at 0, given that it started at minus 4, and that's 1/16. We'll use this number in a bit. Here we plot the probability for the object to end at x, given that it started at minus 2. We saw a plot like this in parts 1 and 2. We can note that the probability for the object to end at 0, given that it starts at minus 2, is equal to 4/16. Here is the case where the object starts at x equals 0. We saw a plot like this in parts 1 and 2. We can see that the probability for the object to end at 0, given that it started at 0, is equal to 6/16. And here are the final position probabilities for when the object starts at x equals plus 2. We also saw a plot like this in parts 1 and 2. The probability for the object to end at 0, given that it started at plus 2, is equal to 4/16. And finally, for the case where the object starts at x equals plus 4, we show a plot of the probability for the object to end at x, given that it started at plus 4. We can read off the plot that the probability for the object to end at 0, given that it started at plus 4, is equal to 1/16. Okay, let's get back to the problem we're trying to solve. The object ends up, after 4 steps, at x equals 0. We want to know, given its ending location, the probability that it started at x equals minus 4, x equals minus 2, etc. Let's look at our Bayes theorem relation. We'll start by calculating the probability that the object started at minus 4, given that it ended at 0. Okay, so let's write down our Bayes theorem equation for the probability that the object started at minus 4, given that it ended at 0. So the probability that the object started at minus 4, given that it ended at 0, is equal to the probability that the object will end at 0, given that it started at minus 4, times the probability that it will start at minus 4, divided by the probability that it will end at 0. There are 3 factors on the right-hand side of this equation which we need to get. The easiest of the 3 factors on the right-hand side of this equation is the probability that the object will start at -4. The 5 possible starting locations were equally likely. Taking all the possibilities as equally likely is called using a flat prior. So, the probability that the object will start at -4 is equal to 1/5. Okay, next, let's get the probability that the object will end at 0 given that it started at -4. We saw from our plot before that the probability that the object will end at 0, given that it started at -4, was equal to 1/16. That's the second of the 3 factors that we need. Okay, so we now have 2 of the 3 factors we need for the right-hand side of our Bayes theorem equation. But we still need the factor in the denominator on the right-hand side, the probability that the object will end at 0. Let's take one more look at our Bayes theorem equation. Let's specifically look at the numerator on the right-hand side. So that's the probability that the object will end at 0 given that it starts at -4 times the probability that it starts at -4. Let's note that this equals the probability that the object will start at -4 and end at 0. This will help us get the probability that the object will end at 0. So the object must start at exactly one of the 5 predefined locations. So the probability that the object ends at 0 is equal to the probability that the object starts at -4 and ends at 0, plus the probability that the object starts at -2 and ends at 0, plus the probability that the object starts at 0 and ends at 0, plus the probability that the object starts at +2 and ends at 0, plus the probability that the object starts at +4 and ends at 0. We can calculate each of these terms in the same way that we got the probability that the object starts at -4 and ends at 0. So we had that the probability that the object starts at -4 and ends at 0 is equal to the probability that the object would end at 0 given that it starts at -4 times the probability that it would start at -4. The probability that the object ends at 0 given that it started at -4 we got from the x = 0 bin on our plot of the probability that the object ends at x given that it started at -4. The probability to start at -4 was 1/5, and the same will be true for the terms for the other starting locations. So, in order to get the probability that the object ends at 0, which is the sum of these 5 terms, we can take the probabilities from the x = 0 bin of our plots, multiply them by 1/5, and add them up. So in terms of the quantities in our plots, we have that the probability for the object to end at 0 is equal to 1/5 times the sum of these terms. So the probability that the object will end at 0 given that it started at -4 plus the probability that the object will end at 0 given that it started at -2, etc. Let's briefly see what this looks like on a plot. Here we've taken our previous plots, multiplied the probabilities by 1/5, and stacked them on top of each other. The different colors represent contributions from paths with different starting points. So here, paths that start at x equals -4 are shown in purple. In red, we see the contribution from paths starting at x equals -2. In dark blue, we show the contributions from paths starting at x equals 0. In green, we see the contribution from paths starting at x equals +2. And in light blue, we see the contribution from paths starting at x equals +4. So, for example, the probability for an object to start at x equals -4 and end at x equals 0 is the probability for the object to start at -4 times the probability for the object to end at 0 given that it started at -4. And that's equal to 1/5 times 1/16, which equals 0.0125, which you can check agrees with the plot. Okay, so putting in our previous numbers, we get that the probability for the object to end up at 0 is equal to 1/5 times these terms, which equals 1/5 times 1/16 plus 4/16 plus 6/16 plus 4/16 plus 1/16. And that just equals 1/5. We can see that this result, that the probability for the object to end at 0 equals 1/5, agrees with our plot. Okay, now we can go back to our Bayes theorem calculation. Okay, so we had our Bayes theorem relation. We had that the probability for the object to start at -4 was 1/5, and we just found that the probability for the object to end at 0 also equals 1/5. So our relation simplifies to the following. The probability that the object started at -4, given that it ends at 0, is equal to the probability that the object will end at 0, given that it started at -4. Quite a simple relation. The cases for -2, 0, +2, and +4 are analogous. So, for example, the probability that the object started at -2, given that it ended at 0, is equal to the probability that the object will end at 0, given that it started at -2. More succinctly, we can say that the probability that the object started at x, given that it ended at 0, is equal to the probability that the object will end at 0, given that it started at x. Here is the plot we had before of the probability for the object to end at x, given that it started at 0. But we just learned that the probability for the object to have started at x, given that it ended at 0, is equal to the probability that the object will end at 0, given that it started at x. So we can just rename the plot. So we have that the probability that the object started at -4, given that it ended at 0, is 1/16. The probability that it started at -2, given that it ended at 0, is 4/16, etc. So we saw in this case that the probability that the object started at x, given that it ended at 0, is equal to the probability that it will end at 0, given that it started at x. But it is important to know that this would not hold if we had used different prior probabilities for the starting locations. We got this result because we used a flat prior. Now, we should make one technical note that this result also wouldn't have worked out if we had looked at an ending location other than x equals 0. But we could have gotten similar results for other ending locations if we had taken the range of starting locations to be wider, so much larger than the region x between -4 and +4. Okay, so here we used the same prior probability for a range of starting locations. We used a flat prior. Why is this interesting? Let's take a quick look at measurement uncertainties. For simplicity, we'll look at Gaussian measurement uncertainties. Let's say we want to measure some quantity, which we'll call Q. For example, Q might be the distance to a star, or the concentration of a chemical in a sample, etc. We don't know the true value of Q, but let's call it Q true. When we measure Q, we'll get some value, which we'll call Q measured. Because of measurement errors, our measured value Q measured will almost certainly not be equal to Q true. Instead, there will be some difference between the true and measured values. We often take these measurement errors to be Gaussian distributed. We'll call the measurement uncertainty sigma Q. This means if the measurement were repeated many times, the values of Q measured would be Gaussian distributed around Q true. So, for example, in about 68% of cases, Q measured would fall within 1 sigma Q of Q true. Under the assumption of Gaussian errors, if we know Q true, we can give the probability distribution for Q measured. However, when we do a measurement and acquire the value Q measured, what we really want to know is Q true. So we can ask, given the measured value Q measured, what is the probability distribution for the true value Q true? This is analogous to the random walk example we saw here. Measurement errors are approximately Gaussian distributed when there are many sources of error which are of similar size and uncorrelated. Some sources of error will push Q measured up from Q true, and some will push it down from Q true. In the random walk example, the starting location is analogous to Q true, and the ending location is analogous to Q measured. A step is analogous to one of the sources of error. In the random walk example, we didn't know the starting location, but we knew the ending location. From the ending location, we wanted to assign probabilities to the possible starting locations. To do this, we had to have our prior probabilities for the different starting locations. We took all of the possible starting locations to have the same prior probability, so we used a flat prior. In the measurement case, if we know Q measured and want to determine the resulting probability distribution for Q true, we also need to assign a prior probability distribution for Q true. A particularly common choice of prior is to take all values of Q true to be equally probable. Just like in our random walk example, this is what is known as a flat prior. In the case of Gaussian errors, and using a flat prior for Q true, Bayes' theorem tells us that given Q measured, Q true will be Gaussian distributed around Q measured. So, just like before, we can take our previous plot and just relabel it. So, we started by taking Q measured as Gaussian distributed around Q true. But using Bayes' theorem and a flat prior, we got a posterior probability distribution for Q true. It is Gaussian distributed around Q measured. We emphasize that just as in the random walk case, this result depended upon our use of a flat prior. Other choices of assumed prior would have resulted in different probability distributions for Q true. If you would like more details, we recommend that you watch the video How to Interpret a Scientific Measurement with Gaussian Error Bars and the 4-part series Why Bayes' Theorem is Important, both of which are available on this channel. Okay, so let's summarize. In this series, we've looked at a particular use of Bayes' theorem using an example of a random walk. We've seen how our choice of prior affects our results, and we've specifically looked at the case of a flat prior. Finally, we related this to the interpretation of measurements and their uncertainties.